Okay, so we're revising the 2016 Common or Open June paper. And remember, we started with a problem that, just to quickly draw it, looked like this. And I've given you the memo of it. Okay? Now, you guys must get very good at looking at past questions, and then you must know the algorithm. That means the method of solving it. Okay, so the method of solving it. So for example, when you saw this problem, so when you see a problem like this, there's immediately an algorithm or way of solving it. We've given you the solution. Let's just go over the algorithm again. So please take this down. Okay, what is the first thing we're going to do when we see that problem? Okay, let's start here, Mikhail. When you see a force that is at 20 degrees to the horizontal.
The opposite of force. I leave my pencil case here.
When you see a force that is at 20 degrees to the horizontal, what are you going to do? Right. Just take that down, because obviously we can't work with forces that are at funny angles. Everything must be in the direction, one direction or the other. Excuse me? The one you did yesterday. What number question is it? It is question number... Question number 2. Okay, question number 2. So the first thing that we're going to do is convert the 35 Newton force to its horizontal component. Okay, and then we did that and it came to 32.89. Right. Everyone with us so far? Yes, sir. Okay, this is question 2. Cassie? Cassie, are you ready to answer a question? Now, once you've got this working in the direction, is this a vector problem?
Yes, sir. Yes.
Okay, so then, if it's a vector, choose the direction that it's going to go in as positive. So it's going to move in one direction or the other. Choose direction system moves in as positive. So, which direction did this move in, Aneli?
Sorry, sir.
Which direction did this move in?
To the right, sir.
Okay. In this case, right, positive.
Yes, sir.
Okay, Tatiana. Are we going to work out all the forces that are in left and right direction? Okay, it's not possible to do this problem unless you've worked out all the forces left and right. Yes. Okay, so we know somewhere we're going to find all forces left and right. Is that very difficult to do? Not really. And then number 4, they're going to ask us a question regarding friction. Fk, it's on your data sheet, I believe, equals mu normal force. Now, if they're asking us a question like that, if they're asking us a frictional force question, so and they gave us the u thingy was 0,14. Then we know the normal force, which is going to be the force acting up and down, is going to be mg. But what was the catch with this? What was the catch with this? Do you remember from yesterday?
So you said that it won't move, so
Do you remember the catch? It's not just mg. Is there a vertical component to this that's also pulling it up as well as pushing it down? So we've got to take that into account. That's the only thing that complicated this problem. Then we worked out the friction. If you look it up, here I work out the friction came to 2.44 newtons. So the friction, which direction was it? Was it the friction left or right? Left. Okay, so your friction here came to 2,44 newtons left. Okay, so we worked it out, no problem. Now, let's get on to working out the tension in the string. So, and as long as you've taken into account there's a vertical component and a downward, we've got to get our normals, got to take that into account. We've got weight and we've got something putting it up. Okay, fine. Just remember it if you get a problem like that. Now we come to the tension in the string. What are we going to do to solve tension in string problems, Anna? Can you just say it a bit louder? Sure. So we're going to find the tension in this string, which pulls this way and this way. It's in both directions. This is pulling it this way, this is pulling it that way. So we're going to find the tension in the string, we're going to use F net equals M net, total plus A total. I can't really use net, but as long as you know we're looking at everything. Are we going to then, Jamie, get the total acceleration of the whole system? And it came to 2.17 meters per second right. So here was the acceleration came to 2.17 meters per second right. Using all the forces. Now, Sonelli, where do we go from there? So we've worked out the acceleration of the whole system. Now, what are we going to do next? So then, once we know the acceleration of the whole thing is just 2 meters per second right, what are we going to do next to find the tension in the string? Any ideas? What formula are we going to use? Same formula again, but using it with respect only to which weight? To the 2 kilogram weight. Sonelli, does that make sense? Let's think why. If we've got this, and we're trying to find the tension in the string, can we use the forces that are acting on this equals the mass of this, so the force of the two, the mass of the two, times the acceleration of the two. And then we can work out the forces of that are acting on just the 2 kilograms. Does that make sense? Does that make sense, man? Because we got to make sense of this. Does that make sense to you? Okay. Well, let's do it this way.
That makes sense.
How many forces are acting on this?
Two.
Okay. Let's carry on. How many forces are acting on that particular weight? Yeah. Which two? Can you see forces acting on it? What is the force upwards called? So there's one force of tension, and what's the other force? Energy. So we got an weight, force of weight. And so if we add those forces, what's the mass of this? We know it is 2. We've worked out the acceleration of it, which is 2.17. And therefore we know the weight, because it's mg. And therefore we can work out the tension, and that's how we do the problem. Okay, let me explain. Friction is when something pushes down, the weight will increase the friction. But if there's a component up, it's going to reduce the weight. So we must, the one is the weight down, the other is the force up. So we've got to subtract the one from the other. I know, that's why we go through it, so that when you see it in the exam, it's not a surprise to you. So that is how you do these string problems. Or take the problem to Mr. Yankees and ask him to explain it his way with simultaneous equations. That's another possibility. Okay. Now the next problem that we gave you was a circuit problem.
So can I ask you a question, please?
Sure.
We get lower gravitation in paper.
We're going to get gravity, I'm sure. So we want to go over these problems. Okay. Now, with our circuit problem, it was very easily resolved. They gave us a resistor. Now, here again, what is your algorithm? Your algorithm is you look for a component which gives you 2 of Ohm's law's values. In this case, we had the resistance and we had the voltage, which was also 4 volts. So if we've got 2 values, we can work out the third. All circuit problems tend to work out like that. I want to ask you folks, if you want to, tomorrow afternoon, we want to go through a few more, this type of problem, a few more circuit problems. If you prepare to come 2 hours and we can go through a few more past papers so you can get more used to this. Remember that this is for your own benefit. It's going to last you forever. Are you prepared to give yourself 2 hours in the afternoon? Think about it. I'll ask you just now. So we see you last period tomorrow.
Yes, sir, you can do.
So that's about 1 hour, but we want to go over a few more question ones, because an hour just goes, or 3/4 of an hour goes by very quickly. If this is the most important thing you can do, is to go over past papers and see the algorithm or way of solving the problem. So please write this down. How do we always solve circuit problems? We look for a component that has got 2 of Ohm's law's values. I just want to move this. Was there anyone here who was able to solve that problem by themselves, the circuit problem? So, did you solve the circuit problem by yourself? So let's get a bit of practice with that. Okay, what's the algorithm? That was, what question was it? Question 11. Write this down. All circuit problems. Look for one component with 2 of volts, amps, or resistance. If you've got any 2 of those, you could work out the third by Ohm's law. By Ohm's law, work out the third. So what did we have? We had a 4 ohm and a 4 volt. Therefore, we worked out amps equals volts upon resistance equals 4 upon 4, 1 amp. So that was very simple, and then our ammeter was somewhere down here. So that is the first secret to solving circuit problems. Then what was the second thing that we did? They asked you what was the combined current when 2 wires split or combine. So what was the rule? If a wire splits or joins, what is the current? How would you phrase it? The current in the one wire is equal to the current in both wires, if you add them up. So that is how we solve that problem. Let's write it down. If we have one wire split into 2, the current in the one wire equals the current in the other 2. Have you got that written down? Okay, question 3. We have a space station with a mass of 2,000 kilograms circulating above the Earth. They first say, state Newton's law of gravitation in words. Now here's like part of the algorithm. If they ask you to state a law, are you going to use that law?
Yes.
Right. So in this case, 3.1, what is that law? Okay, so they ask us to state F equals G M1 M2 over R over D squared. Can you put it in words?
No, can you?
Okay. So we're going to expect you to be able to say, if you have 2 objects, there's a force of gravitational attraction between the space station and the Earth. So let's put it in words. You state what type of force. It's a force of gravitational attraction. It's between 2 masses. The force is directly proportional to both masses and inversely proportional to the distance between their centers squared. Now notice what I said, between their centers squared. So the distance is measured from the center of the Earth to the center of the space station. You're going to need that because they're going to try and get you to work out this distance, the height above the Earth. Now, how do we solve this problem? It says, if the Earth exerts and they give you the force, so we've got the force, we know that, we know the one mass, here's the problem. When I first read this problem, they didn't give us the mass of the Earth, and I said to myself, I cannot answer this unless they give us the mass of the Earth on our BFF. And I looked, and yes, on the front page, they give you the mass, so we've got that Therefore, we can work out the distance between the space shuttle and the center of the Earth. In this case, they say, what's the gravitational attraction between the space station and the Earth? There's only two objects mentioned here.
So they mentioned the Earth in our world, not using
It says, if the Earth exerts a force on the shuttle, there's your two objects. But if they hadn't given us the mass of the Earth, we couldn't have done the problem. But it's there in your BFF. So easy enough to do. And then 3.3, they say, a small station which has double the mass. Okay? Now watch how you solve this. I was showing, there's a girl in grade 11, I don't want to give her away her name, she was asking a question like this. And I was telling her, if you get case 1, and then you get a second case F2, where you have G, a different mass, and a different distance. How do you do it? And I showed her, and I'm just going to show you briefly how you do it. It says a small space station which has double the mass of the shuttle. So you say 2m1. If that is m1, and m1 is the space shuttle, if we have a second case where it's 2m1, you write case 2, and she said, why must I write case 2? Well, we got this case and then we got a second case, which means a second example. And we're going to compare case 1 with case 2. So it says there's twice the weight, orbits at a distance twice that of the shuttle. Twice that of the shuttle. So what has happened to our D? It's become 2D squared in case number 2. Just read the question. Do you understand what I'm saying? So in our first case, which is this, but now we have a second case where we have something orbiting twice the distance and twice the mass. So this is no longer, this was D, it's now 2D, twice the distance. How do we work out what happens to the force? Now, look what I've done. I can say case 2, and I put in my numbers 2E. Then I told her, take all the numbers to the left. F2 equals G equals 2 squared, which is 4. I'll just write 2 squared. G M1 M2 over D squared. Now look at that. Is that, so we had twice the mass, twice the distance. I take my numbers to the left. There's the 2 times the mass, there's 2 times the distance, but don't forget to square it. So I've now got 2 upon 2 squared, which is 4. So now I do the maths, I cancel that, and I find that 2 upon 2 squared is a half. Is 2 upon 2 squared a half? Okay, it's equal to a half of that, but that is F1. So now, case 2, the force is half F1. Make sense? So that's how you solve those problems. So let's just write what we do as our method or algorithm. Let's write what we've done here. If given 2 cases, put numbers in case 2. There I put my numbers. Move numbers to the left. There I move the numbers to the left. And then say Now say, what was numbers left times case 1 or F1, and that is exactly what I've done. Any questions? Do you see how easy that was to do?
So is it because you square? So is it because you square the middle and the distance? So therefore you must take the 2 over and.
It's everything, don't forget to go square. That's the only way they can catch up. Are you guys writing this down?
Sir, is that an R over 2?
So Danny, are you writing?
Sir,
Write it down, please. Write it down.
is that an R over 2?
Where?
There, down, the answer.
1.
Oh, 1.
So 2 upon 2 squared is a half. So our case 2, where this station is double the distance and double the mass, is half of the force. Okay, now let's go to question 10. You are given 2 graphs. The one is current, the other is voltage. When you see voltage upon current, okay, you've got 2 of Ohm's law. When you see any graph where you've got the vertical over the horizontal, do you know what the slope is equal to? Okay, the slope is vertical over the horizontal. So if you've got volts upon amps, any bells ringing? Volts upon amps? Resistance. So the slope of the graph is the resistance. This is one temperature, this is another temperature. Okay. Now, Shakili, which slope is greater? This one. Therefore, which resistance is therefore greater? Number 1. So now, this is what they say. This is what they say. You've got 2 of the same resistors at different temperatures. Which one is the higher temperature? So, we've set the stage. You've got a graph of volts upon current. The slope of the graph is your resistance. We've got 2 resistors. Now we've already established this has got the greater slope, therefore that's the greater resistance. There's only one piece of knowledge that you need to know. If a wire gets hot, does it get a greater resistance or a lesser resistance? And this is just something you need to write down. A wire that gets hot has got a greater resistance. Therefore, T1 is the hotter wire. Let's just say the greater the 10, the greater the resistance. Because T1 has the greater slope, it has the greater resistance. Therefore, highest temperature. Did you see how that problem was solved? Did you see how that problem was solved? Okay.
So, but I don't understand because, I mean, if the mix is what, doesn't it mean that from the wire this current flowing, so how will it increase the resistance?
Look, normally current flowing through it causes the heat. I don't know how you can get a wire that's colder
Of course.
unless you cool it. So maybe they put a cold rag on it to cool it. That's the only way you can get two wires with the same resistance that have got it. So they must have cooled T2, something. But a current flowing through a wire causes it to get hot.
And so therefore you can ease over the resistance.
So this is very hard to set up in practice because I've never seen really a way that you can cool a resistor. Well, I mean, there must be a way, but I've never even seen it. Okay, can I ask you for tomorrow? Look at the latest sheet that I gave you, see what you can do, read over it. Now I'm telling you, it is super important to go over past questions. Now that you've gone over these, I know that if you were paying attention, you would be able to figure this kind of problem out. You may be able to figure out your circuit problem a little bit better out. You would be able to figure out your pulling a mass, Newton's 2 problem a little better. So take that, the rest of that 2016 June paper and start working through it now. See if you can figure out how you're going to solve the problem. And then maybe if you've got the time, do it. It's super important. It's the one thing I could not get my students to do last year. And that is the one reason why students fail. They do not work through past papers. Now, I just want to compliment again this one girl in grade 11. She comes and bugs me all the time to do problems for her. Now, that kind of attitude, I guarantee you she's going to be an A student.
She is an A student.
I guarantee you in matric she's going to be an A student because she is taking the trouble of herself. It's not her parents or her teachers telling her. She's just coming before school, after school, during break. I love it. I think it's super. She comes and bugs me, and I think it's the highlight of my day that some student is interested enough in science that they will come, and she's been doing problems very similar to this in grade 11. So full marks to her. Those are the kind of people I met in Sittenbella, Matiso, in Oscar and Petha, right there in the townships when I taught there. In those township schools, you will find excellent students who, irrespective of the teacher they've got, will come every time, every day with questions for you. And those are fantastic students. They're the ones who are going to fix ESCO.